Moving on to Objective 6.2, we're going to be looking at calculating angles and distances on a map. So I'm going to use the NTS sheets that we talked about previously as my first example on how to actually use the map and the grids in order to carry on. So I will be teaching the UTM coordinate system in more in the next module. I think it's in module 7. So I will be getting more into detail about that, so don't get too hung up on what is a universal transverse Mercator grid. All you really care about right now is that there's units and that the units are in meters. So that's what is most important. So the UTM, which stands for Universal Transverse Mercator, that is a type of mapping grid, and it uses meters as its unit. So here is a map. It's got grid lines on it. So on any NTS sheet, you're going to find that there's some numbers along the top. Generally, they're blue. And so you'll see here that it starts with, like, it says 283,000 meters east, and down here we have 5,458,000 meters north. So we have a northings and an eastings, and these grid lines are all a rectangular Cartesian grid. So each of these lines, each of these grid spaces are 1,000 meters apart. And so you'll see that it says 83,000, and then it's 84,000, and then 283,000, and saying 284,000, 285,000, all the way along here, and it does the same down here along the y-axis. So they're all 1,000 meters apart. So like I said, the numbers correspond to the grid lines. And so if we are looking at, like for example, this corner here, we need to figure out what are the coordinates. So if we start with the eastings, we're going to go across the top here, and we see that it's 283,000 meters east, going down that, all the way down that line. And then here we have 5,458,000 meters north, and we go across here. So that would be my answer. So here's the eastings, or the x-coordinate, which is 283,000 meters, and then the northings, which is 5,458,000 meters. And that would be, sorry, I moved past that really fast. And that would be my coordinates that are left there. So when I mention those numbers, we look for these bigger, like, numbers. They're just a larger font size. They're not bolded or anything like that. But that tells us what numbers are changing along the edge. The rest of them stay the same. And so unless it like resets at like 99 and then goes to 00, then we know that it increases at that point. But that's what we're looking at in a NTS sheet. So here, if we are looking for coordinates and we wanted to find the coordinates of this location, so my screen capture software may cut off these numbers a little bit, so I apologize about that along the bottom. So let's start with the easting. So it is at 576,000 meters east. And so that's where 76 is along this line, and then we have 77, 78, 79, and 80. So we know that this bolded bigger line here is 580,000 meters east. And then along the y-axis, we're going up. This one says 5,654,000. And then we go up to here because that's the line that is attached to, so it'd be 5,655,000 meters north. Well, my answer, 580,000 meters to the east, and then 5,655,000 meters north. Now what happens if we have coordinates in the middle of somewhere, like for example in here, and what we have to do is use a map, scale, and interpolate. Like I said, these scales are never going to go away on you. So we need to find, for example, this spot here. So we're looking at where these two roads come together at this intersection and where that red star is. So what are the northings and eastings coordinates there? So the first thing we need to do is we need to measure the distance from the grid line to the star. Okay, so this one's measured at 5 millimeters. And then we need to figure out what that distance is using the scale. Well, this is an NTS sheet. We know that NTS sheets are, especially the topographic ones with this much detail, are 1 to 50,000. You do need to know those. And then, so we have the 1 to 50,000. So we multiply our 5 millimeters by 50,000 and we get 250 meters. And then we're going to subtract it from the value along this line. Again, my screen capture software may have cut this off. So this line here is 560,000. And so we take 250 meters that we calculated from previous. We subtract that from the 560,000 and we get 559,750 meters east. So that is how we find out the x-coordinate. Then we do something similar with the y. So we measure the line there, and then we find out that it is 2 millimeters. So we multiply it, convert it to the ground distance, and we find out that 2 millimeters times 50,000 gives me 100 meters. And then now, because I'm going up, and I can see the numbers are going up, so we know it's 4,282,000, and it's going up, so we add the 100 meters. So we get 4,282,100 meters north. So my final answer is written in this bright red, which is 559,750 meters east and 4,282,100 meters north. And that's my final answer for that. So what in the next important thing is coordinate calculations. So if you need to go from Cartesian coordinates to polar coordinates, these are the two equations. That's the word I'm looking for. So my radius is my Pythagoras theorem. So it's c squared equals a squared plus b squared. So here we have the square root. Now this x here is my a squared and this is my b squared. We always, as I mentioned in a previous module, we always have our last point first and our first point second. Sorry, I know that you guys probably can hear the screaming in the background. My kids decided to get loud. Anyways, okay. So the final point is the first, and then the starting point is the second. So it doesn't really matter too much here because we are squaring it, and then so that the symbol doesn't really matter. It's going to matter here though in the angle. So the radius, we can also think of it as the distance, and that's exactly what it is. Okay, so x and y at the end point, x and y at the starting point. Then at the angle down here, we have tan. Now, because we are going off of the y-axis, this makes it confusing because we are used to SOHCAHTOA, right? So TOA is opposite over adjacent. And oftentimes in the arithmetic version of the coordinate systems, the y actually goes on top. Because we are not dealing with arithmetic and we are actually dealing with with a geographic coordinate system, the x goes on top instead. So we go the starting point minus the end point of the x on top, and then the starting point minus the end point of the y on the bottom. We take our arctan of that and we get our angle. So this is opposite from what you were taught in high school, and I'm very aware of that because we're doing it from the y-axis in a clockwise direction instead of the opposite. So I'll show an example of that on my whiteboard here in a moment. Then we have the reverse, so we have coordinate calculations, and here we have polar to Cartesian. And so my change of x is my radius times the sine of the angle. My change of y is the radius times the cos of the angle. Again, remember that you are going from the y-axis. That is why it is opposite from what you have been taught before. So if you have starting coordinates, if you have one coordinate where you start at, you can use that to determine the end point, which is really handy if you're traversing in surveying, or if you're using laser scanning and you have to follow some sort of particular path. So you have your starting coordinate of x, and then we say our radius times the sine of the angle plus x1, and then y2 is radius times cos of the angle plus y2, or y1. And that's where you will get those values. And that's the reason, because x2 minus x1, I can add x1 on either side, and then I get x2 alone on this side of the equation. So let's switch to my whiteboard so that we can work with it. And here is what we can work with. So let's say that we have a point. So let's say my point A is located at, I'm going to use some values from the UTM so that we can work with that. So that's 543,219 meters and 563,251 meters. Okay, and then, so that's point A, and then I have point B at the next coordinate, which is at 781,377 meters, and we have it at 32 seems to be stuck in my head today, 9498 meters. Is that too many? Nope, that's good. All right, so those are my two numbers. Those are my 2 points. So my suggestion is always draw these out. Okay, so if we do this, we can do it this way. So here is my northings and this is my eastings. So if I have 5, let's say this is, 5 here, 6, and I'm going to just shorten this down a fair bit because of the numbers are so big. And this one is, let's go 3, 4, 5, 6. Okay, so what I'm doing is I'm shortening this down to just the numbers that matter. So in this case here, I am using these numbers in the X, and then I'm using these ones as my Y reference. So if you're wondering what I'm doing and what my thought process is on that, I'm just saving myself. So point A is just about between 5 and 6 in the X, and then it's around 6, a little bit above 6 in the Y. So if I put that there, this is my point A. Now if I go to point B, I see that it's gone down or gone along higher to a little over almost 8. And then this one has gone down in the northings to 3. So here we're going to go about here, which is B. So now what I need to do is I want to determine my polar coordinates. Okay, so we're going from A down to B, and that's the direction that we are going. So often I will say polar coordinates A to B. Okay, so that means vector. So now we can figure out what is the radius. So the radius is the easiest one to start with, because radius equals the square root of delta x squared plus delta y squared. So my radius equals the square root, and we're going to make this really long because it's big numbers. So we got the end point, and if you do this as a habit, it makes it much easier when it really becomes necessary. 3,219 squared plus the 5329498 minus 5632511 squared. And then we're going to calculate that through. So I'll give you guys a moment to calculate that, and then I will give you guys the answer. So as you've put that into your calculation or your calculator, or if you're using any other software to do that, the answer, the radius, is equal to 385,403.829 meters. Okay, so that's the radius. Now if we want to figure out what the angle is, we have to use tan. So the angle, theta, equals tan negative 1. And I said the x goes delta x over delta y. So we have 781,377. This is where making sure that x2 comes first is really important. And you'll see why in a moment. So 5329498 minus 5632511. And I'll give you a that should have tan negative 1 here. Give you a chance to calculate that. And theta equals negative 38.16615 degrees. Negative. Well, we don't like working in negative angles because that makes it really confusing. But why did it become negative? So what I'm going to do is I'm going to take my A to B. So I have A going down to B, B and A. And then what I'm going to do is I'm going to draw a little coordinate system on A. Okay, so we have this, and A is going to be my origin. So my angle is, actually here. So my angle is like that. But this is at negative 38. So that means that it has to be going the wrong direction. And that's what that negative refers to. It's going the wrong direction. So it's actually going like this. So we have an issue right here that we have this value that's not actually representative of going from the correct axis, right? So in order to get this into the correct value, you cannot just add 360. I know a lot of the times we just add 360. It doesn't work that way in this type of math because this is going the opposite direction. And so therefore adding 360 is just going to put it in some weird location. So what we're going to do is we actually have, if we do the full angle here, that's 180. So theta is equal to 180 minus, it's actually adding this 11615 degrees. Okay, so it's adding the negative. So it subtracts it off so that we can actually get this angle in here. So when we do that, I get 141.8338 degrees. Now this is in decimal degrees, so we want to switch that into HMS. So this becomes, once we've done that, 141 degrees and 50 minutes and 02 seconds. And there is my theta, and here is my radius. Okay, so that's how you do from Cartesian coordinates to polar coordinates. And then if we want to do this the opposite way, so let's say that we have point A, we have a town point A, and it is at 73478 meters east and 5613948 meters north. Okay, so there's point A, and we know that point B is found at 798.6 meters at an angle of 191 degrees, 13 minutes, and 42 seconds. Okay, so this is an azimuth. This is my distance. So it's not very far, which is fine. It doesn't need to be very far to be able to go. But that's where my point B is. What are the coordinates? Are point B's coordinates. Okay, and that's going to be in my rectangular coordinate system. So first thing I'm going to do is I'm going to tackle this. I'm going to put 191, 13, 42 into decimal degrees because that's how my calculator handles it. So I'm going to go like this, and that equals, give you guys also a moment to do it. And I get 191.22833 repeating. That's going to give me my decimal degrees. And then, now that I have my decimal degrees that I can work with, now I can work with the formulas that we had. So delta x was equal to the sine of the angle, and then that's multiplied by r. Okay, and then so if we wanted to go x2, it equals to r sine theta plus x1. So we have r, we have the theta, and we have x1. So equals 798.6 meters times sine of 191.22833, and then plus x1, which is 734,768 meters east. And that gives me 191. That gives me 734,612.497 meters east. Now, I apologize if you hear like the dogs in the background and such. They actually want to be in the room with me, but they're being really loud, so I'm trying to keep them out of the room with me so I can video properly. Then they're scratching at the door and everything else. It's become quite annoying actually today between kids and dogs. So working from home, the pleasures of working at home. Okay, so once you've calculated that, there's my answer. Does it make sense? And that I always tell you to, does it make sense to check it? So we have my coordinate system. Here's my point A. Well, actually, no, that's not do point A there. Oh no, undo. I need my eraser. Okay, so there we go. So here's point A is at 7 something over here and 5. So we're just going to place A over here. So we know that A or B is 191 degrees. So somehow B needs to go at 191 degrees, which is a little bit further past that. So B has to be like over here somewhere, right? Oh, not 7. That's supposed to be a question mark. So B is over there. So does it make sense that this value went down by a little bit? Yes, it does, because it should be more down than it is over with the change in direction. So that makes sense to me. So we're good there. So let's move into delta x, or sorry, delta y. So we're trying to find the y coordinate of point 2. This equals the cos theta times r. Or we go y2 equals r cos theta plus y1. And we do the same thing as we did before. Except this time we get to use cos. And the y. I'll give you a moment to calculate that. So I get 5,613,164.686 meters north. Now, does that make sense? Has it gone down? It went from 948 meters down to 164 meters. So that makes sense. So I would say that this looks correct. So my point B is located at 734,612.497 meters east, and with the northings 5613164.686 meters north. And that is your answer. So that's how you convert between rectangular coordinate systems and the polar coordinate systems using the coordinates. And in the next video for objectives, we'll get into objective 6.2. I will show there will be another video showing how to do coordinates again using the maps that you have for your workbooks, and I'll have that using the ruler, and you'll actually see it in action as well.